So, welcome everyone to today's tutorial lecture. So, this is actually tutorial 3. So, today we will see how to perform DC simulation using cadence and how to characterize a MOSFET through DC simulation. So, the outline of today's class is basically the outline is basically an introduction to DC simulation in cadence. So this is the basically outline of today's lecture. So the most of the time of the lecture we will spend in the cadence software. So let us go to the simulator. Okay, so we're now in our simulator. So we need to draw the schematic in this way, and I am using here 45 nanometer technology. So now you see inside this MOSFET, I am considered the length as a variable parameter. Also width as a variable parameter. So we consider this here and click OK. After that, we will consider here a DC voltage source. So this is also a variable, right? VGS of N. That means gate voltage of the NMOS. And similarly, the drain voltage. This is actually we will set as a VDD. Okay, so let's apply an OK. So if you try to find out what is the minimum length and width for the 45 nanometer technology, so let us find a MOSFET. So press I from your keyboard, and you have library here. So click on browse, and after that you get your GBDK45, this library. So you need to add this one. Then you find your cell NMOS 1 volt, and then you can place in your MOSFET and left click on your screen. It will be feed your schematic window, and if you press the escape button, then it will go. So if you see here, so how do I see the parameters? So select the MOSFET and press Q from your keyboard. So press Q. So you can see the values, length and width. These are actually minimum. Length is 45 nanometer and finger width is 120 nanometer. So let us delete the MOSFET. And also similarly you can find the voltage source and the ground. So how do you find that? Again press I from your keyboard and go to the library option. Now select the analog lib. From here you write the VDC. So if you write the VDC, you can see your voltage source here, and you can plug in value inside the voltage source also here. Okay. Finally, if you need ground, you will write here G and D. So G and D means ground. Okay, so and routing, if you want to try to routing something with something, it's very simple. Press W and start your routing. Okay, you need to press W from your keyboard. Alright, so we need to delete this wire. Okay, so after finishing the schematic, you need to check and save it. If everything is fine, from your CDS log window, you can see everything is saved. That means no problem. And after that, you will go out to the launch and click on the ADEL. No, nothing is here. Then what you do? So you actually declare some variable in your schematic. So you need to call those variable here. So copy from cell view. Copy from cell view. So now you can actually assign your desired value here manually, and by assigning your value, your W and L value will be changed. So what is the advantage? Advantage is we not need to go the schematic frequently to change the length and width. So if we declare those things as a variable, and if we change the design variable, these are the design variable, then automatically it will change the internal length and width values and voltage source value, or whatever actually it is. It depends on actually what you basically declared as a variable in your MOSFET or voltage source or whatever. So let me just give the minimum length. So this is 45 nanometer, and minimum width, which is 120 nanometer. Initially I give this, and let's say my VDD is actually 1.2 volt, 1.2 volt, and my gate voltage is 500 millivolt. So I assume these things, and then we are doing our analysis. So now let us do the DC analysis. So click here, select the DC, then save DC operating points, click on the design variable. So I want to sweep my VGS. So select the design variable as VGS and click OK. And sweeping range is suppose 0 volt to 1.2 volt. VGS, so it is 1 volt. It will be enough. So here we are consider the sweep tab is automatic. Click on apply and then OK. So let us run the simulation. Okay. So if the simulation is okay and fine, so now you want to find out the values of this MOSFET. For example, its beta effective value, its mu and Cx value, and all the parameters you want togetherly with a list for the MOSFET. So how do you do that? You will use the results, then go print, and from here you will select the DC operating points. And after that, the cursor will be go on your screen. Just select the MOSFETs. So basically, you will see all the values here. Your beta effective value, B effective value, C dB, C dB. Each and every value is here. Your ID, and you see here threshold voltage. So everything is there. So this is a way to find out the DC operating points, and you can collect your data from this table. And second, there is a method. If you go to the view and then annotation, and from here you will select the DC operating points. So if you click here, you will also see some parameters like ID, your VGS, your VDS, your transconductance. So this value are actually showed. So if you want to add something more, go to from annotation to setup, and this is your library, and these are your cell. So click on cell and select the NMOS 1V because you have just 1 volt NMOS, and see your parameter. So this parameter you are actually chosen. That's why they are actually showed here. If you change this parameter and select different parameter, let's say I change the I want to add suppose a new parameter, suppose called the threshold voltage. So just write here VTH, and the VTH will be added and it will display here. And let's suppose you want to try to find out the beta effective or the region of this operation of this MOSFET. So let us change the VDS and write here region and click apply and OK. So now you can see your new adding value. The MOSFET is operating in region 3 and the threshold voltage is also showed here. So this is another method. If you want to display your operating points, you can follow this procedure. So our main objective is basically find out all the parameters of this NMOS. That means we want to characterize the MOSFET. So we need all the values of the MOSFET. So that's why we will add here a SCS file. So there is another type of method which you follow. Then you will get combined set of data. Those data are actually your DC operating points data, and they are very advanced data. So let us see how to you add the SCS file. So if you have no SCS file, then you cannot see any combined set of data for this NMOS. So if you go to tools and result browser and select the MOSFET and go to the DC. So in this window, you actually get all the values. But right now you have no SCS file. So that's why you have no regular value, irregular value. So these are regular values. So you did your irregular value. So if you want to add the irregular value, you need to go your workspace, library, and then from here create a new document and click on empty file and rename this file from your perspective. All right, for your perspective, and then click on .scs and then click on enter. Okay, so I already have a .scs file, that's why I delete this one. So this is my NMOS char. I rename this and it is a .scs file. So now open this folder, and inside this folder you need to write these strings. So if you see here, this is my nm0, right? So that's why I write here nm0. So just write save nm0 such that all, and click on save and close it. So that .ss file creation is actually done. Now you need to add the .ss file in your simulation. That means you need to connect the .ss file with your simulation file. So click on the ADEL and go to the setup option. From here you need to select the simulation files, and you need to add your simulation files here. So stimulus file it may be used. So click on this table row and with a dot and go your workspace, and my library name is GMOVerID and I rename as NMOS underscore char .scs. Click it OK and open, and after that select this one, apply, and then OK. So now it's time to run the simulation again. Okay, the simulation is done. Now go to the results, tools. From here, result browser. Now click on this and the DC. So now you can see all the irregular values here with the regular value also. So these all values are actually your DC operating points value, and we need to find each and everything from here. So if you see here the ID, that is the current. So click it and select the plot signal. So you can see the ID versus VGSN plot here. Just simply click on here. So as you know from the previous tutorial video, we need some parameters. So if you recall the parameter, which parameter is actually we need. So in the previous tutorial video, I was explained that the by default plot will be generated with respect to VGS because I sweep the VGS, and Y will be my different parameters. So this will be the by default curve, and my parameters are ID, VD set, GM over ID, then ID by W, then FT, then FT into GM over ID, then GM then GM versus GDS. So these all are my parameter. So this all value we need to extract from cadence, especially the ID, the VD set, GM over ID, ID by W, FT, FT by GM over ID, and GM versus GDS. So these all are my important characterization parameters. So we can see that from our simulation, that is all the time these all parameters value will plot with respect to VGS, but this is not our objective. Our objective is that we will plot these all parameters with respect to GM over ID. That means ID versus GM over ID, VD set versus GM over ID. We need this plot, not this. But cadence provide me this plot, but I need this plot. So how do I generate this curve? We will explain this in the next tutorial video. But in this tutorial video, basically we try to find out these parameters and plot these parameters against VGS. Is that clear? So let's go again the cadence. So at first we want to add the ID. So ID versus VGS plot we can see here. So let us click this and send it to the calculator. And after that, send it to the buffer expression. So you can see the output and name it as a ID. So click change and the next. Okay. Now if you run your DC simulation, you can see your plot. That is in your y-axis ID and your x-axis is VGS. So if you see here, if you increase your gate voltage, the current will exponentially increasing, drastically increasing the current. If you change your VGS, suppose if you click on from your keyboard B and right here, suppose 500 millivolt. So at 500 millivolt, you have 8.33.299 nanoampere amount of current. But if you increase your gate voltage, then the current will be increased drastically. For your 900 millivolt gate voltage, you get 36.0405 microampere amount of current. So you can analyze your plot by using this vertical line. Just press V from your keyboard, and if you want to the horizontal line, you can use H from your keyboard. So in that case, you can modify your y-axis value. Suppose you need 800 microampere current, let's say. So here is actually maximum value is 55. I cannot, we cannot allow 800. So suppose I give here 55 microampere of current. and just place it okay, so let us write 45 microampere current. So this is the line, and this line will cut here, and the corresponding point is if I delete this, so the corresponding point is 962.27 millivolt. So if you apply here this amount of gate voltage, you can reach the 45 microampere current. Okay, so now let's try to find out our more parameters. So let us find the GM. So if you try to find out your GM, where is the GM? So this is the GM. So click on it, go to the calculator and set it into the buffer and modify this. Let us write here GM. So let's run the two plot togetherly. So we can see here the two different plot. So GM is the for the red green one. So let's click on the curve, send to measuring. Symbol measurement. Move to new window. So you can see the GM versus VGS curve. So from this curve, you can observe that if you increase your gate voltage, your transconductance will be increased. All right. So that is important parameter. We can find this from the result browser. So we need more parameters like GDS. So let's find to the GDS. From here you need to find the DC, and then here is the GDS. So send it to the calculator. So basically we need GM versus GDS, not the just GDS only. So we can do at first we clean the stack and then find out the GM and set it to the calculator and click here. Then again go to the calculator, find out the GDS, go to the calculator and divide it by it. So you can see here this is your GM by GDS. So if you want to try to plot, you can click here. So you can see this is your GM by GDS versus VGS. So this is your curve. So let's send this expression to the buffer and rename this as a GM versus GDS. Okay. Then we need ID versus W. Right. So how do we can find the W? We have ID, right? So if you again write the expression of the ID and then divided it by W, so you need ID. So this is my ID. So let us send it to the calculator and save it here. So now we need our variable. So let us find out here. Okay, this operating point. Vs for increase this is voltage. So this option var means variable selection point. So click on here and click on the MOSFET and list, find out WN. So we need this WN. So let's divide it by ID versus W. So let us plot it. So we cannot understand what is ID versus W and what is the another plot. So we need to move it the stack. Sorry, the buffer. And then we can rename this. So we can write here ID divided by W. Alright, so now we can plot the ID divided by W. So you can see that this is your ID divided by W curve. Alright, so now we need to find out more parameters. So we need to find the main parameters, that is the GM over ID. So go to the DC and find out this is the GM over ID. So you directly get the GM over ID, but if you want to create GM over ID, in this case you select GM and ID individually, then divide those things. So I am using here GM over ID value. So send it to the calculator, and after that send this to the buffer expression, and then write here GM over ID. So apply and OK. So let us see the GM over ID versus VGS plot. All right. So this is my GM over ID versus VGS plot. So we can successfully extract some values. Now we want to find out the FT. FT means transient frequency. So the expression of the FT is GM divided by 2 pi into CGG. Here the CGG is total gate capacitance. So let us find out the FT. So now we need to find out the FT versus VGS. So we need the expression of GM, copy it, and then go to the tools, result browser, and from here we need to find out the CGG. So go to the DC and find out the CGG. So this is the CGG. Send it to the calculator and then paste the expression of GM and divided it. and then multiply this whole things with 2 pi. So 2 into 3.1416. And after that, close the parenthesis. So let us plot, is it okay or not. So this is actually work. So send it to the buffer, or you can click on the get expression also, and right here this is as FT. Click on change and then next and OK. So where is my FT? So again go to the calculator. From the calculator we select the get expression, and this is right as FT. Add, apply, OK, and now plot it. So this is my FT versus VGS curve. Okay. So finally we need the FT into GM over ID. So let us copy the expression of FT and go to the calculator. Already I have FT expression, so I need to copy with it FT into. So let us consider a whole bracket. And this whole term will be multiplied with GM over ID. So this is my expression of GM over ID. So copy it and then paste it. Okay. And then click it, edit, and get expression. And write the expression name as FT into GM over ID. Click on apply. Okay. So now let us run the FT into GM over ID versus VGS. So you can see the curve like this. So basically this is the way that we actually follow right now, and by using this concept we can find out the parameters very easily, which are actually we will use for our end calculation. So finally, if we try to plot everything togetherly, and run it, you can see all the curve. Okay, so these are my all curves. Here ID, GM over ID, ID versus W, GM by ID. So all the curve is here. So if you see the GM by ID, just click on it and go to move to new window. So you can see the curve individually also. So in this tutorial, I actually try to cover these things. That is the basic fundamentals of DC simulation. And I think that video was helpful for a student. So now I am save these things. So save state, click apply, okay. So this will be saved. So this is the wrap up time of today's tutorial video. In the next video, I will show more things in details. And with this, I conclude this segment. Thanks for watching.